Okay, hi everyone. Sorry I'm not here today, but please give the sub all the respect that he or she is due. Okay, so we're going to start out with the do now. If you notice, the homework is a worksheet, another 6 problems. I'm going to give you a take-home quiz tomorrow. Okay, so let's start out with the homework. And now we're going to start out with the homework, I'm sorry. We're going to start out with our do now. So you might want to pause this for a second while they have a chance to try this. I'm going to keep going. Okay, so we want to find the area enclosed in the first quadrant by the graph y equals x cubed, which just looks like that, and the graph y equals x. Wow, didn't do such a great job with that. All right, that's a little better. But we're just talking about the area in the first quadrant, so we're just talking about this area right here, the area of that region. So remember, the way we find area is we add up the areas of rectangles. Rectangles have area of height times width. When we use vertical strips, which is what we were doing the other day, the width of each strip is an infinitely small change in x. So that would be dx. Put that here. The height of a vertical strip we get by taking the y-coordinate on top minus the y-coordinate on the bottom. The y-coordinate on top is the y on the line y equals x. So y on top equals x, minus the y-coordinate on the bottom, which is right over here, that's y on the cubic. Y on the cubic equals x cubed. So we've represented the height of any of these rectangles drawn in this region in the first quadrant. Y top happens to be y equals x, y bottom is y equals x cubed. And we have to find the limits of integration. We want to add up these rectangles from the smallest x, which looks like 0, to the greatest x. And to find those, we set the function equal to each other. Because when they intersect, y on one, which is x cubed, must equal the y-coordinate on the other, which is x. To solve that, we get them equal to 0, and we can factor. Now we can further factor the x squared minus 1, x minus 1, x plus 1. So there are actually 3 points where these two graphs intersect, and the x-coordinates of those points are 0, 1, and negative 1. So for our region, we're interested in using 0, and the x-coordinate of this point would be 1. Yeah, the x-coordinate of this point would be negative 1, but we're not going to need that. So the limits of integration, we're going to add up these rectangles starting at x equals 0, going up to x equals 1. And that's it. Now we just got to get the antiderivative of x would be 1/2 x squared, x cubed minus 1/4 x to the 4th. Then we draw the line, evaluate it from 0 to 1. You give yourself some parentheses. You first plug in the upper limit. 1/2 times 1 squared is 1/2, minus 1/4 times 1 to the 4th is 1/4. And when we plug 0 into both of those, we get 0. So our final answer is 1/2 minus 1/4, which equals 1/4. So the exact area of that region is 1/4. Okay. Now next, I'm giving you the homework answers, and you can take some time to pause this and look over those. I've also given you the written out work for some of these that the substitute will distribute. Now, the other day, we ended the lesson talking about how sometimes using vertical strips might not be ideal or might not even be possible. And I gave the example of having these two, what we call sideways parabolas. And if you remember from the last example C of our notes on day 71, we saw how it would be kind of a pain having to break it up. And so even though it's possible to do it this way, you'd have to use two different integrals, one integral from 0 to 1, and then another one from 1 to 3. You could do it. But what I'd rather talk about today is how, by using horizontal rectangles, you can make your life a lot easier. So to get area, again, we're just adding up rectangles, height times width. But if we draw our rectangles or strips horizontally, now, if you recall, to get the height, we take the x-coordinate on the right and we subtract the x-coordinate on the left. Remember, anytime you want to find the length of a horizontal segment, you take x on whatever x equals on the right minus whatever x equals on the left. And as far as the width of each of these goes, it's just an infinitely small change in the y-coordinate. It's a small change in y. So if we have, let me just see if I can move this. So the idea is this. We can find the area by summing up with a definite integral from the smallest y-coordinate to the greatest y-coordinate. Now remember, so when we're using horizontal strips, we're going to have to add up from bottom to top. We're going to be interested in the y-coordinates of the points of intersection. So we're going to add up from the smallest y, which we'll call C, to the greatest y, D, of the region. Whatever x equals on the right, in this case I called it some w of y, and then minus whatever x equals on the left, which I called v of y. But that'll be your x right, whatever x right equals, but it'll be in terms of y, minus whatever x left is. dy is your width, and for your limits of integration, smallest y to greatest y. Okay. So we're going to do that problem C that I kind of introduced and we ran away from the other day because we agreed it would be difficult. So we're going to start with the same graph. We're looking for the exact area enclosed by x equals y squared. Now, if you don't know what that looks like and you want to enter that into your calculator, you have to break it up to two functions. Y equals the positive square root of x and y equals the negative square root of x. The other one's also quadratic. It will also be a parabola. And this, for this other parabola, let me just label this one first. The greatest x will ever be is 3. So this one is going to go the other way. So it'll start at 3, and then it'll go the other way. All right, so this parabola is x equals 3 minus 2y squared. But the beauty of using horizontal strips this time is that no matter where I draw my representative horizontal strip, x right always falls on the parabola x equals 3 minus 2y squared, and x left always falls on the parabola x equals y squared. It's not like x right changes or x left changes, so we can get away with one integral. So we're going to start by saying, to get area, we sum up height times width. And when you're using horizontal strips, the height is going to be whatever x is on the right minus whatever x is on the left. And the width, I don't know if you remember, the width, if your horizontal strips now, is going to be a small change in y, dy. And that's important. That tells you that the only variable that you should see in your setup should be y. So even though I'm saying x right minus x left, I want to know what x right is in terms of y. So if we look at our strip, x right is x on this parabola, and x on this parabola equals 3 minus 2y squared. So in for x right, I'm going to write in 3 minus 2y squared. X left always falls on this other parabola with the equation x equals y squared. So x left is x on this parabola, which is equal to y squared. So the height of any of these strips that I've drawn here can be represented, if we combine like terms, to 3 minus 3y squared. Now, what's the next thing that we need to know to finish this off? We need the limits of integration, because we want to add up all these rectangles starting down here at the smallest y value, and then we're going to keep adding them up. Just picture them going across all the way up to the greatest. So I need to get this y coordinate down here, and I need to know the y coordinate up here. Now, if you want to know the y coordinates where two graphs intersect, set what x equals on one equal to what x equals on the other. Because when they intersect, both coordinates are the same, including the x's. But if I set what x equals on one, which is 3 minus 2y squared, equal to what x equals on the other, y squared, I'm saying they have the same x coordinate where they intersect. And now I can solve it. Let's move everything over to the right. So we'll add 2y squared and we'll subtract 3. So 0 equals 3y squared minus 3. 0 equals 3 times y squared minus 1. Which is 3 times y minus 1 times y plus 1. So when they intersect, the y coordinate equals 1 or negative 1. So those are the important values to know. Down here where they intersect, the y coordinate's negative 1, and up here where they intersect, the y coordinate's 1. I don't need to know the x coordinates. Remember, this is a dy problem. I want to add these up from smallest y to greatest y. So those are my limits of integration. Once we have the setup, now we can just get the antiderivative. And by the way, if you are going lazy and you go to your calculator now, you just enter it in like it's x's. The calculator doesn't know what's on your paper. If you wanted to use Math 9, you could do that. Just pretend that they were x's. But we're going to do this one out. So we get the antiderivative, which is 3y minus y cubed, negative 1 to 1. If we plug in the upper limit of integration, we have 3 minus 1. If we plug in the lower limit of integration, 3 times negative 1 is negative 3. Negative 1 cubed is negative 1, so minus negative 1 would be plus 1. So we wind up with 2 minus negative 2, which equals 4. That would be the exact area of that region. So much easier with one integral because we decided to use horizontal strips. Again, we could have used vertical strips, but it would have required two integrals because y top changed and y bottom changed. So we needed to break it up that way. Okay. Example D. Find the area of the region enclosed by the curve y equals the square root of x. Let's just sketch this out. Y equals negative x plus 6. So that's a line with a y-intercept of 6 and a slope of negative 1. So we would cross here like it's 6. And then the line y equals 1. Let's put a 1 here. 6 here. So just to be clear, let's just shade that in a little so we can see what we're going for. We're looking at this region. I need a small one. So we want to find the exact area of this region. Now, if we decided to use vertical strips, we would need two integrals because y top changes at this point here, which I'm trying to draw. Okay, so you would need one integral to get the area to the left and then one integral to the right. That's why whenever you have a point of intersection on the top of the region or the bottom, Using horizontal strips will avoid you having to use two separate integrals. So we're going to use horizontal strips. Okay, that's just one to represent them. And since we're using horizontal strips to get the area, of course we're doing height times width, but the height will be x right minus x left, and the width will be dy. It will always be, when you use horizontal strips, x right minus x left for the height, and dy for the width. So let's fill in what x right is. X right would be x on this graph. And x on this graph, if you look at the equation, it's y equals negative x plus 6. So we're going to have to solve for x. Let's add x to both sides and subtract y. So we have x equals 6 minus y. So I just didn't have that handed to me, okay? If I knew it was x on that graph and it wasn't already x equals, I had to solve for x to see what it equals. So we can fill that in. 6 minus y. Minus x left. Well, x left, that's the x on this graph. And the equation for that graph is y equals the square root of x. So on that graph, x equals y squared. You have to solve for x right and x left sometimes. Not always. Sometimes they give you what x equals. Okay, so we have our height. Now we need our limits of integration. We need to go from the smallest y of my shaded region. Well, that I can get from the graph, because remember, it starts at y equals 1. But I have to figure out, so I know the lower limit of integration is 1, right, because this is 1. This is the line y equals 1. But I want to figure out what the y coordinate is up here, because that will be my upper limit of integration. You want to add up these horizontal strips from the smallest to the greatest y. To find that upper limit of integration, I want to set what x equals on the line equal to what x equals on that part of the parabola. You set the x's equal if you want to solve for y. So x on the line, we already figured out was 6 minus y. That's got to equal x on this curve, where x left is, and on that curve, x equals y squared. So getting it equal to 0 again, we can solve by factoring y plus 3, y minus 2. So we get two values. We get y equals negative 3 and y equals 2. The reason we're getting two values is because if we had continued and drawn the whole parabola, the line would have intersected with the parabola at negative 3 also. But the part we're interested in is this upper part. So the upper limit of integration is this one. So y equals 2. All right, now we can get the exact area. We take the antiderivative. So it's 6y minus 1/2 y squared minus 1/3 y cubed from 1 to 2. We plug in the upper limit, the lower limit, and subtract. If we plug in the upper limit, 6 times 2 is 12. 1/2 of 4 is 2, minus 8/3. We plug in 1, we have 6 minus 1/2 minus 1/3. Maybe we'll try combining like terms. And here we have 10 minus 6. So if I take, this is 10 minus a 6, that's 4. Here I have negative 8/3 minus 1/3. Oh wait, sorry, that's plus 1/3. That's negative 7/3. And then I still have plus 1/2 because minus 1/2. All right, that didn't really, oops, plus 1/2. And I gotta watch the minuses, right? Okay, so let's see. I guess we'll deal with 6. So we have 24 6 minus 14 6 plus 3 6. 26 minus 14, that's 12, plus 3 is 15 6. 15 6 can be reduced because 3 goes into both of those. It goes into 5 halves. So 5 halves would be the exact area, if I didn't make a mistake. Check it out. Oh, wait a minute, shoot. Oh, what did I do wrong? 12 and 3 is 15 6. No, it is 15 6. I think I'm right today, not that day. 12 minus 14 is, oh no, 12 minus 14 is 10. I take that back. Whoops. Oh, shoot. Oh, let's take that back. Oops, 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 oops. All right, right at the end there, kids. See, I wasn't feeling good. Oh, 24. Wait a minute. I had 10 minus 6 was 4. 4 is 20. Oh, I wrote 26 6. That's where I made my mistake. Sorry about that. 24 6 minus 10 6. Okay. So, I had to check. All right. So we have 13 6. 13 6 is the exact area. Sorry about that. Okay. Next one. 8. I think this is the last one. I don't want to spend too long. Okay. Find the area of the region enclosed by the curve x equals y squared. That's this. And y equals x minus 2. So that line would have a slope of 1 and a y-intercept of negative 2. So something like that. This is not exact. And so we're looking for the area of the enclosed region. So all this area. Okay, so we're going to use horizontal strips because there's a point of intersection on the bottom. And if we tried to use vertical strips, y bottom would change from one graph to another. That's why using horizontal strips is the best way. That way you only use one integral. So area will be the integral of x right minus x left. Width of any horizontal strip is going to be dy. So first, we got to figure out x right. Well, x right is x on this graph. X on this graph is x on the line. If you look at the equation for the line, we can get what x equals by adding 2 to both sides. So x on the line equals, I'm sorry, I'm just not thinking straight, y plus 2. So x right equals y plus 2 minus x on this graph, that's going to be your x left. Well, that one's already done for us. That just equals y squared. And we're going to add these up from whatever the y coordinate is down here to whatever the y coordinate is up here. Because remember, dy problems, horizontal strips, you're adding them up from smallest y to greatest y. So to find the y coordinates where two graphs intersect, you have to set what x equals on one equal to what x equals on the other. And on one of them, x equals y squared, and on the other, x equals y plus 2. When we set them equal and get it equal to 0, factor, we get y equals 2 and y equals negative 1. Okay? So our limits of integration are going to be from down here, this little question mark here, the y coordinate down here is negative 1, so we're starting to add up these rectangles down here, And we want to add them all the way up to up here where the y coordinate equals 2. So from -1 to 2. Okay, now it's a nice easy problem. So now we're just going to get the antiderivative, and half y squared plus 2y minus 1/3 y cubed, or y cubed over 3, from -1 to 2. And again, if that point you wanted to check it with your calculator, you just put it in the calculator using Math 9, using x's instead of y's. Then we're going to set up a parenthesis for plugging in the 2 and then the -1. 1/2 of 2 squared is 1/2 of 4, which is 2, plus 2 times 2 is 4, minus 8/3. -1 squared is 1, so that's just a half. 2 times -1 is -2, and then it's going to be plus 1/3. See if I get this right this time. So if I combine the like terms, the 2 plus the 4, and this is really going to be a plus 2, that's all together, that's 8. 2, 4 minus -2, that's 8. Then we have -8/3 minus 1/3. That's -9/3, or minus 3. And then we still have minus 1/2. So 8 minus 3 is 5, minus 1/2 is 4 1/2, or 9/2. So, just to sum up everything, to find the area between two curves, sum up the areas of an infinite number of vertical or horizontal rectangles. In general, area equals the sum of height times width, the integral from a to b of height times width. When using vertical strips, the height is y top minus y bottom, and the width is dx. And the limits of integration are the smallest x value to the greatest x value of the shaded region. When using horizontal strips, the height is x right minus x left, and the width is dy. And the limits of integration are the smallest y value of the shaded region, to the greatest y value of the shaded region. Okay, well, good luck with your homework tonight. I'll see you tomorrow. Bye.